So in this video, we're going to look at Einstein's special theory of relativity. Now, the magic of physics is it begs us to take a look at everyday experiences and, on peering more closely, start to peel away some of the assumptions that we take for granted and look at them a little bit more carefully. And there's no better example of this than looking at Einstein's special theory of relativity. But first we have to go back to what Galileo and Newton had to say about relativity, because they're the ones that first used the notion of relativity to define motion itself. Now, as an observer looking to measure my motion, what I'll need is a clock to keep track of the time and a ruler to keep track of my position as it changes over time. But again, physics begs us to look at observations a little bit more closely. So the first thing we can start with is looking at what it means to be moving. Now, I'm sitting at a computer screen making this video. I'm presuming you're sitting at a computer screen watching this video. So from my perspective, I'm sitting motionless, and I'm assuming that you're doing the same. And yet we both are, I'm making the video on the Earth. I'm assuming you're watching this video on the Earth. And the Earth is spinning around at a pretty high rate. Where I'm at, we'll use round numbers, but it's about a 24,000 kilometer trip to go around the Earth at my latitude and come back to the same place. And I do that in 24 hours. So that means that I'm actually moving at 1,000 kilometers per hour as I'm standing still. So it introduces a wrinkle to what it is that we mean by motion. Now, we've already said that we need a clock to keep track of time and a ruler to keep track of distances. But in order for me to know that I'm moving, I can't hold on to the clock and hold on to the ruler at the same time. I'm going to hold on to the clock to keep track of the time, but I've got to let go of the ruler and move past the ruler to know that I'm moving, because otherwise, if I hold on to the ruler and get rid of any other perspective, I have no idea that I'm moving. But even with this sense of motion, it begs the question, which one's moving? Is it me or is it the ruler? Now, to get a better sense of which one's moving, we need to add some other piece of information, some backdrop that we'll refer to as a frame of reference. And this tree off in the distance will serve as that extra piece of information, that frame of reference. So this way, I'll know that when I'm moving, the ruler stands still with respect to the tree. And when the ruler's moving, I'll stand still with respect to the tree. And so it's all relative. We need two frames of reference in order to gauge motion, and the two frames of references may not agree with each other on which one is moving, but as long as both frames of reference are not accelerating, or we refer to these as inertial frames, then Newton's laws of motion hold true, and we refer to this as Galilean relativity. Now enter Albert Einstein. He took the groundbreaking work of James Clerk Maxwell and his understanding of the electromagnetic nature of light and the measurement of the speed of light by Michelson and Morley, and he came up with some startling conclusions. And from these conclusions, he developed the postulates of the special theory. As an extension of Galilean relativity, Einstein reasoned that not only were the laws of motion true in all inertial frames, but so too were all the laws of physics. And unlike other motion that's defined by the frame of reference, light doesn't need a frame of reference to define its motion. In fact, the speed of light is the same in all frames of reference. Now we can imagine a timing device that's made up of a pair of mirrors, and an observer watches a photon bouncing back and forth between these to keep track of time. And we'll add a second observer, and we'll call our observers A and B, and they'll watch this timing device together. And since they're in the same frame of reference, they'll share a couple of key observations. They'll observe the distance that the photon travels, and they'll agree on the speed of light. And of course, the time it takes for the photon to travel is related to these two pieces of information. And because they're both in the same frame of reference, they'll agree on the speed of light, they'll agree on the distance that the photon traveled, and of course, they'll agree on the time that it took. But let's analyze the physics when our two observers are in frames of reference that are moving with respect to each other. Now, to compare the observations from the two different frames of reference, we need to remember where the photon was in the beginning. Now, observer A sees the photon move the same distance, but observer B sees the photon move on the diagonal. Now, if the speed of light is the same for both observers, and they can't agree on the distance, then they must necessarily disagree on the time that the photon takes to travel. Now, let's say the relative speed between the frames is that of a fast spaceship, defined by the distance separating the two frames after a period of time measured by observer B. And rearranging this equation to solve for the distance the spaceship travels, we can connect this with the photon distances of each of the two observers, because these vectors form a right triangle. So using Pythagoras and our knowledge of the speeds and the distances, we can now compare the times experienced by each of the observers. So let's take a look at the algebra of Pythagoras, where the hypotenuse squared is the sum of the squares of the other two sides. And now we can expand each of the terms on either side of the equation. And then we can collect the like terms and then divide each of the terms by the speed of light squared. Now we can factor out the square of the time from observer B's perspective, so we can compare it directly with the square of the time from the other frame of reference. And of course, taking the square root of both sides of the equation allows us to compare directly the time experienced in each frame of reference. Now, since observer A is holding the watch, Einstein referred to this as proper time, denoted by t sub 0, or t naught, whereas observer B's perspective of time is viewed as relativistic time, or just t. So relativistic time and proper time are used in Einstein's equation. So the upshot of this is the faster we move through space, the slower time passes, and this is referred to as time dilation. So let's see what this lengthening of time does to our perception of distance. And for that, we'll go back to our watch and our ruler, moving through some frame of reference. And of course, to compare perspectives, we need to add a second observer in that other frame of reference. And of course, these reference frames are moving with respect to each other, so that observer A sees B moving with respect to her frame of reference, and observer B sees observer A moving with respect to his frame of reference. Now, A is holding a clock, so she sees proper time, whereas B sees time relativistically. But B holds the ruler, so he sees proper distance, and that means A must see distance relativistically. But that speed that the two observers see as the same is what we're going to use to compare these two perspectives. And bringing these two expressions together and then rearranging them, I can now compare directly the way they experience distance because I already know the relationship of the two different time perspectives, which we now know as time dilation. And if we bring these two expressions together and rearrange them algebraically, we end up with a new expression comparing the two perspectives on distance based solely on the relative speeds of the frames of reference. Now, unlike time, which lengthens, as speed increases, distances actually get shorter, and this we refer to as length contraction. Now, there's a YouTube video called The Ultimate Speed by Dr. Bertozzi at MIT that shows electrons moving in a lab 8.4 meters in 33 nanoseconds. Now, these are seen from the lab perspective, so we have proper distance and relativistic time. So first, let's find the speed that the electrons are traveling, and for that, we'll use the proper distance divided by the relativistic time, which of course is our 8.4 meters divided by our 33 nanoseconds, which gives us a speed of 2.54 times 10 to the power of 8 meters per second, or about 85% of the speed of light. Now we'll see the significance of using this fraction of light speed when we put it into the determinant of our relativistic equations. So now let's look at time from the electron's perspective, and for that we'll need to rearrange the time dilation expression. So we'll multiply each side by the determinant to isolate the proper time, and now we substitute numbers and simplify that v squared over c squared because c squared is now common to both the numerator and the denominator in that expression, and this gives us a proper time of 17 nanoseconds. And now we can find the relativistic distance experienced by the electron from the length contraction equation, where we'll substitute numbers and simplify that v squared over c squared term again and find a relativistic distance now of 4.4 meters. And finally, we can check the speed as seen from the electron's perspective by using relativistic distance and proper time, and sure enough, this agrees exactly with the speed experienced by Dr. Bertozzi in the MIT lab. So Einstein says that time slows down at high speeds, but I thought time was supposed to fly when you're having fun. Sorry, couldn't resist.